For part A, the cylinder has a height of, let's say, h, and we're going to look at a tiny spot on a cylinder. So this tiny thing has a mass of dm and a volume of dv. It is at x distance away from the center, or that's its radius. And the radius of the whole cylinder is, let's say, r. Density equals to m over v, but it can also equal to dm over dv. The dm over dv represents that small blue circle, while m over v represents the whole cylinder. I'll be using dm over dv because I'm gonna use the integral expression of inertia, so I can isolate dm and replace it. So I'll isolate dm, and then you can rewrite dv as the circumference of the blue circle times its thickness, which is dx, and it has a height. So using the integral expression of inertia, we can replace dm. We can move rho, 2 pi, and h out. And we can condense x squared and x to be x cubed. And our bounds would be 0 to r. And by taking the integral, we'll get 1 over 4 x to the power of 4. We'll replace x with r. And replacing 0 in there, we just get 0. We'll replace rho with m over v, but v is equal to pi r squared times h, which is the volume of a cylinder. The r squared cancels out with r squared from the r4. The h will cancel out, the pi cancel out, and 2 over 4 will just be 1/2. So that would get us 1/2 mr squared. For b, we can use set torque equal to each other. So net force times r equals inertia times angular acceleration. Our angular acceleration, we can expand that to, wait, actually no. We'll expand inertia to 1/2 mr squared. We'll keep angular acceleration the same because that's what we're trying to find. And the net force is really the tension, and then times r. We can find tension by doing Fg minus T1 equals to M1A. We can expand Fg by doing M1G. And because we're trying to find T1, we'll isolate it. And we can plug it back into our original equation. Our r's will cancel out. So there'll just be one r. And then we'll isolate angular acceleration. and I'm gonna separate it. And what that would let me do is turn A over R into angular. We'll plug in the numbers. So that'll be 3 times 9.8 over 1 half 30R. Oh, our R is 0.3. 6.533. 1 over 5. I'll move the negative 1 over 5 alpha over to the right side. And then I can add them. 36 or 5. Angular. And then alpha would be 5.44 rad per second squared. For C, calculate the linear acceleration. We can use the function a over r equals alpha. We know alpha to be 5.44. And we already know r is 0.3. So our linear acceleration of m1 would be 1.623 meters per second squared. For D, since angular acceleration is constant, we can use this function. And since it's starting from S, we don't have to include the omega initial times t. Our angular acceleration is 5.44, and the time is 5. That would give us 68.05 rads, but it wants it in revolutions, so we'll convert it by dividing over 2 pi, and that would give 10.831 revs. Now there's a second mass that's hanging on the axle, and the axle is negligible mass. So for E, the line of motion would be at the left because M1 is heavier than M2, and M1 generates a bigger torque because it's farther away from the axis of rotation. So I would do net torque equals I alpha, and net torque is torque 1 minus torque 2 because torque 2 is generated in the opposite direction because it's at side opposite. And I can expand alpha by doing 1 half mr squared times alpha. We can expand the two torques by doing fg1 times r minus fg2 times little r. Oh wait, it's t1 t2 r. Then we can solve for t1 by doing fg1 minus t1 equals to m1a. Then expand that and isolate t1. And for T2 is bigger, so we put that first. Then FG2. Then isolate T2 and expand FG2. So we'll plug that all in. They have for the two blocks, they have different accelerations because they have different radius. So label them as A1 and I'll label this one as A2. A1 can be expressed as big R and alpha. They have the same alpha because they're on the same cylinder. And then A2 would be little r times alpha. So I would replace A1 and A2 with R alpha. And this would be big R alpha. So then I'll distribute the R's. And I'll carry the negative sign over. Now what we can do is move each term that has alpha to the right side. And I can factor out an alpha. And I move everything to the other side to isolate alpha. And then I'll plug in the numbers. So M1 is 3. Alpha would be 5.0758 rads per second squared. For F, what's the linear acceleration of M1? So A1 is equal to big R alpha. Big R is zero point 0.3 and alpha is 5.0758. that'll be 1.5227 meters per second. For G, the cylinder has only kinetic energy rotational because it's not moving anywhere, but it's spinning. The function for it is 1/2 I omega squared, and we can expand omega to be 1/2 mr squared. To find omegas, we can use common form because angular acceleration is constant. And it's falling over a distance equal to 5r, but you can convert 5r into rads by just dividing r. So it'll be 5. Our angular acceleration was 5.0758. And I'll keep the square on the omega because omega is already squared in the KU rotational. So that'll be 15.758. Put that in. And we'll plug in the mass and the radius too. Our answer would be 34.261 joules. To find that work, we add up all the energy. So as it's falling, the 3 kg has a kinetic energy, as well as the 2 kg has kinetic energy, but also potential energy because it is gaining height as it's moving. And the cylinder has K rotational. We can expand that. To find V1, we can use this formula. And since it's starting at rest, we don't need to add velocity initial. Our A1 was already found and set after 5 seconds. So V1 would equal to 7.6. For V2, we can do the same, but our acceleration is different now. So our acceleration can also be rewritten as little r and alpha. Little r is 0.03 and big R is 5.0758. And that'll give us 0.15227. And then times the time, which is 5 seconds. That'll be 0.76135. And for omega, we already know the angular acceleration and the time, so we just plug that in. Point 5.379. Okay, so we plug in all the numbers in. Oh, we didn't find H. To find h, since acceleration is constant, we can use conform. But smarter choice would be using this because time is already given. And our A is the same as A2 because only the 2 kg is gaining height. So we plug in h back in. We'll condense the 2 1/2 into 1/4. Oh, equal to 560.7 joules.